Hi guys. So today we're going to look at solving both log and exponential equations. Now in class we actually separated this into two different days, but we're going to go ahead and put them together just on this one video. So the first thing we're going to look at are log equations. Now depending on the form that your log equation is in, there's a different method you may want to use to solve it. Typically though, a common strategy, if you see more than one log being added and subtracted, you're typically going to want to condense those together using the properties we did last class. So what we learned last class, if you have 2 times a log, that becomes an exponent. So log base 3, now it's going to be 4 squared, which is 16. And then since I'm subtracting those logs on the right side, I can divide the arguments and make that log base 3 of 8. If you have 2 logs of the same base that are equal to each other, all you would have to do at that point is just set the arguments equal to each other, because that's the only way that those logs can be equivalent. Again, this is because they have the same base. All right. Now there may be some extra steps here depending on what your arguments are, but again, you are setting the arguments equal to each other. Now looking at the second example, this one looks a little bit different. This time there are no logs to condense, and not everything in this equation is in terms of a log. So what we're going to want to do instead here is get this log by itself. So what I'm going to do first is add 7, and then I'm going to divide by 2. Then I can rewrite this in exponential form. Okay, so if you have one log, typically to solve it, get the log by itself, then rewrite it in exponential form. On this one, we didn't write it in exponential form because, again, I had a log equal to a log. But since there's only one log here, I want to write this in exponential form. The base of ln is e, so this is going to be e to the 11 over 2 for a power. It's going to equal to x minus 1. Then to solve for x, I would add 1. I would divide by 2. So I get that x is equal to e to the 11 halves power plus 1, all divided by 2. If you did not have a calculator, this is your most exact answer. Okay, and this is actually the form that we would leave it in. Now, if you have a calculator, you can go ahead and actually evaluate this and get the decimal. And that's going to give me 122.846. Okay, so again, non-calculator answer would be here. Calculator answer, you can get to this point. Even though you can get to that point with a calculator, though, you still need to find that exact answer. Okay, it's very important to be able to show the steps to get to that point and still know what this answer is in terms of e. All right, so the information in the box is what we just talked about. Again, just kind of some strategies here. Condense when possible. If there are logs on both sides and they have the same base, then you can set the arguments equal to each other. All right, if that's not the case, then you're going to want to rewrite it in exponential form. Then that last piece of information there, always check for extraneous solutions. This has come up in our last 2 types of functions we've been solving. It's going to come back up here again. All right, let's look at example 3. Again, we have 2 logs, so we can condense those using our properties. So this is going to become the log of x plus 2 times x minus 1. I can go ahead and actually multiply those together, and I can make that x squared plus x minus 2. Now, since again I don't have logs on both sides, I need to rewrite this in exponential form. The base here is 10, okay, because the base is not written. So this is going to be 10 to the first is equal to x squared plus x minus 2. So now we're dealing with a quadratic equation. In order to solve a quadratic, we have to set it equal to 0. Then at this point, I can factor, find my roots, and these are my 2 possible answers. Now remember, we have to check for extraneous solutions. For a log equation, an extraneous solution is any solution if I plug it back into the original equation. If it gives me a negative argument, it is not a solution. So -4 is not a solution. It's not because -4 is negative, it's because when I plug in a -4, it makes the argument of either of those logs a negative number. So as long as one of those arguments is a negative value when you plug it in, it is not going to be a solution. 3 does work, and that is our only solution. All right, so now let's look at exponential equations. With exponential equations, you'll also see a couple different forms. Depending on the type of equation you have is this strategy you're going to want to use. So something like this first one, I am able to actually rewrite these bases in terms of the same number. Okay, they both can be rewritten with a base of 3. Okay, this first one already has a base of 3. The square root of 3 I can rewrite as 3 to the 1/2. Well, that's my new exponent. Power to a power, I multiply. So that's going to get multiplied by the exponent that's already there. At this point, if my bases are the same, I can just set the exponents equal to each other and solve. So I end up with x minus 1 equals 1/2. Well, let's do it this way instead. Let's go ahead and multiply by 2 first. So this is 2x minus 1. Let's go ahead and make it 2x minus 2. I don't know why I did it that way. Subtract 1, and I get that x is equal to 3. Okay. Now, what's important to remember here, a very common mistake is people will see 3 and they'll say, hey, if I just make that a square root, it's going to match. You cannot just rewrite that as 3 to the 1/2 because that's changing the value of the problem. We can rewrite a base in a different way because it doesn't change the value. Okay, 3 to the 1/2 power is still the same thing as the square root of 3. It doesn't change what I actually have. Okay, so again, just be very careful that we are just simply rewriting things. We're not actually changing values or just doing one thing to one side of our equation. All right, so if you feel pretty comfortable, pause the video, try example 5. All right, so we are going to, again, rewrite these two numbers in terms of the same base. The base that I could use is 3, because 1 over 9 is 3 to the -2nd, and 27 is 3 to the 3rd. I would take that exponent and multiply it by the exponent that's already there. And now since my bases are the same, I can just set the exponents equal to each other. And then from here, I would just solve for x. And I get that x is equal to -3/7. All right, so now I'm actually this problem was changed on your notes. Sorry about that. This is actually equal to 6, because otherwise it's a very simple problem. So now we're looking at an exponential equation. I'm going to go ahead and get the exponent by itself. So 2 to the x is equal to 5. At this point, I cannot rewrite these in terms of the same base. So what I'll have to do here then is rewrite this as a log. Okay, so this would become log. The base of the exponent is the base of the log. So it's log base 2 of 5 is equal to x. Now, if this was non-calculator, you would leave your answer in terms of a log, and that's okay. But if this was a calculator, you would be able to actually evaluate that log and actually get that decimal. And I would get that decimal is 2.322. All right, so now let's look at example 7, same idea. Get the log, or get the exponent by itself. So I'm going to add 2, then I can divide by 2, and now my base is by itself. Once my base is by itself, I can rewrite this as a log. Since it's e, I'm going to use natural log. The base is e, so I don't have to write that. It's going to be the natural log of 3 is equal to x over 3. Then at this point, to get x by itself, I would just multiply by 3. So x is equal to 3 times the natural log of 3. Again, if it's non-calculator, you would just leave it in that form. But if you do have a calculator, then you can go ahead and evaluate that and get the decimal, which is 3.296. Again, even if you are using a calculator, you still need to show what that value is in terms of that log. So the last strategy you can use, sometimes instead of rewriting your function as a log, it's going to make more sense actually to take the log of both sides. So whenever we solve equations, we know if we do something to the left side, we have to do it to the right side. If I square the left, I square the right. If I square root the left, I square root the right. So same concept here. What I'm going to do is I'm going to take the log of both sides. That just means I'm going to write log and basically I'm going to make what was on there the argument of the log. The reason I'm doing this is because if I tried to rewrite this using my exponent properties, this would be log base 2 of 3 to the x minus 1 is equal to x. Now it'll still work, and you'll still be able to get to your answer. It just might be a little bit messier. Okay. Now, using our properties, okay, we know that if I'm raising an argument to an exponent, I can take that exponent and move it to the front. So this becomes x times log 2, and then this is going to be x minus 1 times log 3. Now just remember, that whole exponent is being multiplied, so we need to make sure we keep it in parentheses. All right, so now at this point I need to get x by itself. Okay, so that means I need my x's all on the same side. So I'm going to go ahead and distribute and make this x times log 3 minus log 3. Now keep in mind, I told you guys it was really important you did not distribute a log to an argument. This is different because, again, the argument is not what I'm distributing. I'm actually taking the function x minus 1 and actually multiplying the function by the entire log, including the argument. So that is okay to do. Then we get our x's on the same side. Now that my x is on their same side, I can factor it out. And then in order to get x by itself, I would just divide by what's with it. And now I have my answer in terms of log. So if I did not have a calculator, I would stop here. At this point though, if I want to find what that decimal is, I can go ahead and plug this in. Now it's actually okay if instead of using a regular log, if you want to take the natural log at the very first step, that's still going to get you the same answer. So it could be either one of those, but I'm going to go ahead and plug that in to get my decimal. And I get that it is 2.71. All right, so if you feel pretty comfortable, go ahead and try example 9. It's going to be a very similar process. All right, so let's go ahead. Again, you can, if you want to rewrite this as a log, you can. It's going to be kind of messy. So I'm going to go ahead and I'm going to go ahead and take the log of both sides. So this time I'm going to use natural log this time. You don't have to, but I just want to show you that it will still work as long as you do the same thing to both sides. Okay, move the exponent to the front. Okay, I'm going to distribute. I'm going to put my x's on the same side, and I'm going to move everything without an x to the other side. So x natural log of 3 minus x natural log of 7. Then it's going to be negative 2 natural log of 3 minus the natural log of 7. Factor out my x. Okay, and then I can divide by what's with x. Whoops, not divide by x, sorry. And divide all of that. And I am left with negative 2 natural log of 3 minus the natural log of 7 over the natural log of 3 minus the natural log of 7. And then if I had a calculator, I could evaluate that to get the decimal equivalent. Just go ahead and plug that straight in the way it is, and I would get 4.89. Okay. Again, you could take that value, plug it back into the original to get your equation. Now, one thing to keep in mind, okay, you might see this log version, and you might think, hey, I can cancel out those natural logs of 7. Remember from our last unit, you cannot do that. You can only cancel a factor if that factor is in both the top and the bottom. Okay, it kind of almost looks like this factor is, but remember, it's not because this is multiplied by 2. Okay, it is not parentheses around it. If there was parentheses around it, then you could go ahead and cancel it out, but that is not the case here. All right, so the last one we're going to look at is in a very different form. So if you look at this closely, you may see that this looks pretty similar to something that you have seen when we factored. Okay, so this looks very similar to that shape. The only difference here, instead of x, that x is being replaced with e to the x. Okay, so what we're going to do actually is we are going to factor this. But because it's kind of hard to see the factoring right here, what I'm going to do is I'm going to replace e to the x with a different variable. Okay, I'm going to go ahead and use u. And I'm going to say that u is going to take the place of e to the x, at least just for this first step. So if I do that, e to the 2x would be u squared. E to the x would be u, and then minus 6. So then I can factor. This would be u minus 3, and u plus 2. And then if I wanted to solve this, I would just set each of those equations equal to 0 and solve. Okay, so I would get that u is equal to 3 and u is equal to negative 2. I'm not actually solving for u, though. I'm trying to solve for x. So at this point, what I'm going to do is I'm going to go ahead and replace u again. I'm going to put it back where it was. And this is actually how this equation factors. Okay, some of you might be able to get to this point without showing that u step, and that's okay. I just think it's a little easier to see that way. Now, since we have a factor equal to 0, then all I would do is set each factor equal to 0 and solve. So I would get that e to the x is equal to 3, which I can rewrite as a natural log. So the natural log of 3 is equal to x. Same thing over here, e to the x is equal to negative 2. So the natural log of negative 2 is equal to x. And then again, if you want your decimals, you can go ahead and plug those in and get the equivalent decimal. So I get that the natural log of 3 is 1.099. And then if I tried to do the natural log of negative 2, hopefully you saw this before, but this is not going to give you an answer because, again, we cannot take the log of a negative number. Okay, so my only value here would be 1.099. All right, so that's it for logs and exponential equations. Again, just kind of some common strategies for log equations. Condense where you can condense. Okay, for log equations, condense where you can. If you have a log equal to another log with the same base, you can just set the arguments equal. If you only have one log and you can isolate it, then you rewrite it in exponential form. With exponential equations, if you can rewrite them with the same base, then you can set the exponents equal. If you can't, then you need to either rewrite it as a log or take the log of both sides.